Hello and welcome to this lecture. So let me finish with the proof of existence and uniqueness of the exterior differentiation operator on manifolds. Well, we had stopped at this point. So first of all, we defined the operator using local coordinates by this formula. Basically, we push forward the, or rather pull back the form to an open set in Rn, apply D there, and then pull it back to the manifold. And then we showed that this is well defined, as well as, and this way of defining D satisfies properties 1 to 3. I just showed 3 and left 1 and 2 as exercises. Now, note that so the next observation is that to say to get to uniqueness of this, note that D is local. So in other words, if you have two forms on manifold which agree on an open set, then D omega 1 will be equal to D omega 2 on the same open set. So with this in hand, now we can prove uniqueness as follows. So let's fix a chart, any chart on M, and then we know that in okay, before that I should remark that let D tilde be another set of omega I M omega I plus 1 B linear maps satisfying 1 to 3. So suppose there are other bunch of possible candidates for exterior differentiation, which I call D tilde. I would like to show that this D tilde is actually equal to the D that we just defined. Now, the moment you have this properties 1 to 3, this first, the local property just used properties 1 and 2 in the proof. So the local property will continue to hold for D tilde. This whatever argument we just gave in the previous lecture will hold for any operator which satisfies 1 to 3 in the theorem. So with that in mind, let's start. Let omega be any form and you take a chart on M. We can write omega equals AI dxi, where AI are smooth functions C infinity U. Now what I should remark is that right, we can write this, yeah. So the definition of D that we gave, namely pulling it to Rn, applying D there, this definition, the one in the red box, this definition amounts to saying, will imply extend AI x1, x2, xn this is not good notation, so the bracket should come after this AI functions as well as these coordinate functions x1, x2, xn to M. To begin with, AI was defined just on U, and similarly this x1, x2, xn. This x1, x2, xn of course are what one means is by these is that xi at a point P in U is this chart map phi I of P, where phi of P is phi 1P, phi and P. Coordinates just refer to the components of this phi 1 of phi. And right, so one has this, and these are defined again, the xi's are defined only on U, so we can extend them to all of M. Well, right, actually if one wants to be very precise, then one has to take a smaller open set. So this is U, and you pick a point P and then take a smaller open set, a smaller chart U tilde, such that the closure of U tilde is contained in U, and work with and extend it to this AI x1, x2, xn to all of M. In other words, extend it outside U tilde rather than U. The reason being that at the boundary of U, for instance, this xip can go to infinity in Rn. So in order to avoid technical difficulties like that, one normally takes a smaller chart and works with that. So let's assume that we have done that, and the point is that let be the extensions. Now look at this form. Let omega 1 equal to AI hat, then again dx1 dxn hat, oh sorry, xi1, oops, this is not quite correct. D at xi1 dx hat ik. Right, so now apply d tilde to this. D tilde omega 1 equals, well, d tilde is satisfies properties 1 to 3 in the theorem, so therefore one has Leibniz rule, and moreover again d squared will be 0, so by the same argument that we have been using, we get this and this equation is valid on all of M. And of course one is interested in the original form omega, not this omega 1. So, but observe that since omega equal to omega 1 on U, the reason being these are extensions of the AI and xi. So that means they agree on U, and that's what I've written. So therefore the corresponding forms omega 1 and omega will also agree on u. So since this happens, since omega equal to omega 1 on u, we have d tilde omega equal to d tilde omega 1 on u. Well, so in other words, this is d tilde over, but d tilde omega 1, we have a expression for this on all of m. When I restrict to u, this a hat I will become ai and so on. So this is just ai dxi1 dxik. And moreover, yeah, okay, this is what one gets for d tilde. But our definition of d as what I had written earlier, this definition in the red box is equivalent to saying that, that's another way of writing, is implies that d omega is given by, oh, I think I forgot something. Oh, so this dai wedge here too, dai wedge. dai wedge, right. So our definition of d implies that d omega is exactly the same thing, dai dxi1 and the definition in the red box that this is that is equivalent to this definition. I leave it as an exercise, but it's quite straightforward. And so therefore, we conclude that therefore d tilde omega equal to d omega on u. So for any chart, we have proved that d tilde on in any chart d tilde omega and equal to d omega. And that concludes the proof of uniqueness. So well, now another crucial property of D that we haven't formally, that was not mentioned in the theorem is oh right, and also there was the third, in our theorem we said we had three main properties, and I said that the moment you have these three properties, A, B and C also follow. So we already seen, we just saw that the chart expression is forced to be this, and we already seen the local property. And let's see this restriction. If U is in open, then d omega. That's also quite straightforward. It follows from the chart property. Let U be open. So we want to check if d of omega restricted to U equal to d omega restricted to U. So actually, so this again, if you can, there are a couple of ways of doing it. One straightforward way of doing it is just cover you take an open set and put a chart inside the open set, and then work with the left hand, and then just check directly that in the chart that this property holds. So after all, inside the chart, I mean, this expression, the moment you express in local coordinates, this expression will omega restricted to u will have some form, the usual form, something of this type, and then you'll end up getting d of this, which we know is dai wedge dxi and so on. And as for the d omega restricted to u, well, we already know that on a chart d omega is precisely given by this anyway, this expression here. That's the way we define d omega. So there's nothing much to prove here actually. It more or less follows from our definition of d omega. And so now the other thing is, which is does require a couple of lines of proof, is the pullback property. So if f from m to n is a smooth map, and omega belongs to capital omega k n, then I can do f star of d omega. That will be the same as d of f star omega. Again, one can use charts and so on, but there's actually no, yeah. So one can use charts to prove this. In a chart, so let's u phi pc be charts on m and n with f of u contained in V, then f star d omega will be f star. So here for d omega, I'll use the red box definition of d in a chart. So this will be c star d c inverse star omega, and this will be well, what I can do is I can write this as I can phi star composed with C composed with F composed with phi inverse star acting on d of C inverse star omega. And the reason I can do that is, well, I can just take star of this triple composition, the order gets reversed. So I'll get, first I'll get phi inverse star, which will cancel with this to give me identity. Then I'll get F star, then C star, which is what I have here. So it's just rewriting F upper star composed with C upper star in this form. Now this, the point of writing it like this is that this is now a map between what I have here. This thing is a map between open subsets of Euclidean space. And we know that for open subsets of Euclidean spaces and smooth map between them, we know that the star operation commutes with D. So I can write it as C star oops, again I got the red color. So star and then D. So this entire map I can underline map I can take inside the D operation, and I get C compose with F compose with phi inverse star, and I still have this thing here of this. Well, again, if you take star of this triple composition, the whole thing gets reversed, and at the rightmost side I'll get C upper star, but there's a C inverse upper star, so that will cancel to give me identity. And finally I just end up with D of F, well, so this phi inverse star F star omega. And this by definition. So in the first definition we use the expression for D in local coordinates on N. Now we use the expression for D in local coordinates of M. So this is the same by definition, this is the same as D F star omega, which is what we wanted. We started with this and we end with this. So that proves that. So by now we have all the basic properties of D that one usually encounters. There are some more things involving Lie derivatives and how the interplay between Lie derivatives and Lie brackets in particular and D. But since I have not talked about too much about Lie derivatives, I won't go into that. However, I will mention shortly in a relation between D and Lie brackets. So here are some. The first one is relates D with the multivariable calculus, vector calculus as in the classical sense. So when one studies vector calculus, one has these operations, divergence, curl, gradient. So they are very closely related to D, and it's as follows. So first remark, let U be an open set. Then if I start with a smooth function on U, well, I can take the gradient, and what I end up with is a vector field on U. So to be precise, the gradient of a function in classical notation, this is del f by del x, I plus del f by del y, j plus del f by del k, no, del f by del z, k. In our notation, this is grad f is the vector field, del f by del x, del by del x plus del f by del y, del by del y, del f plus del f by del z, del by del z. And once I have a vector field, then I can take the curl of that vector field. So, well, again, one can write down, it's the definition of curl that I'm working with, the same as the classical one. And one gets another vector field. And then one has the divergence operator. which gives us back a function. So you start with a vector field and you get back a function. So right, so these are the three classical operations on functions and vector fields. Now, and I have this maps like this. Now let in the below this I'll write down our D. So this is C infinity U again. D will take me to 1 forms, and then D again omega 2U, and then omega 3U. Well, so now the claim is that if let's use here, I can, of course, both are C infinity U. So I can identify these two spaces just with the identity map. Now here it's called sharp isomorphism. So I'll just put B, and then here there's a map beta which I'll define, and here there's a map star I'll define. So this B, the input of B is going to be a vector field, and out of that I'm supposed to get a 1 form. Well, if I prescribe what that 1 form is at any point as an element of the dual space of the tangent space, then I'd be done. So I define this to be xp in a product V. So here V is in TPU, which is just R3. So this is the way I define a 1 form associated to a vector field. And this is the usual way one goes between a vector space and its dual space in the presence of an inner product. And as for this, beta, this is something which does not involve an inner product. So here beta, so again I start with a vector field. I'm supposed to get a 2 form. So I'm going to act on 2 tangent vectors. And this is defined to be, I look at this 3 form, dx wedge, dy wedge, dz on R3, and then evaluate it on, the input is at the left side there are just 2 vectors v and w, but I'll use xp as the third vector. And this is for all v, w and tpu. And finally, the star map is supposed to start with the function, and I should get a 3 form on u. So star of f, all I do is I just take the standard 3 form dx wedge dy wedge dz, and I multiply it with f, the function f. So this gives me a map. Now one can check that all these are linear isomorphisms between the corresponding spaces. So sharp, beta, star are linear isomorphisms. And moreover, the important thing here is that in a way, keeping these isomorphisms in mind, These classical operations are nothing but D acting on appropriate spaces. In other words, what I mean is, for instance, grad is the same as D, but I have to keep track of these isomorphisms. In other words, if I start with this space, I apply grad and then come back to this by the sharp, then that's the same thing as D acting on identity. So for first grad, the sharp isomorphism composed with grad equals D, the first D, and in the second case, this beta composed with curl of a vector field is the same as D composed with the sharp isomorphism, and in the third case, star composed with divergence is equal to D composed with beta. And from this, one can check that. See, we know that, for instance, that let's give it name D1, yeah, D1, D2, D3. The fact that D2 composed with D1 equal to 0 can be implies, instead of D2 I can put B inverse on this side. After all, B is an isomorphism. B composed with curl composed with B inverse, and D1 I can use this expression, B composed with grad equal to 0. The B inverse and B give me identity, so I get this composed with this is 0, but this B is an isomorphism, therefore I get curl composed with gradient as 0. The classical fact that curl, likewise you will also get divergence composed with curl is 0 by using these two, the last two D's. So all the classical vector calculus stuff can be captured in this formalism of differential forms and exterior differentiation. So I'll stop here and talk a bit more in the next lecture about relation with Lie bracket. Thank you.